So topological entropy. Okay, so yesterday I finished the lecture by mentioning this monotonicity statement for minimal submanifolds. Okay, so let me sketch the proof. Okay, so I was considering the complex affine space of some dimension and a complex submanifold in it containing the origin. And I was looking at the volume of V intersected with the ball of center 0 and T. So 0, the origin is a point of V. So I was looking at this function. I renormalized by dividing by T to the, I don't remember the dimension of V I chose, so let's say 2R, where the complex dimension of V is R. Okay. And I said that this function is increasing. This is the formula that, this was the corollary I wanted to use. So it's an increasing function, and in fact, to prove that it is increasing, I gave a formula involving the pullback of the Fubini's 2D metric. Okay. So for this formula, I will not prove it, but you can look at the book of Jean-Pierre de Mailly on complex algebraic geometry and a complex analysis, when he defines the notion of Lelong numbers. When you define Lelong numbers, you look at this type of quantity where V is replaced by a closed positive current and the volume is replaced by the integral of the Keller form against the current. Okay, so the mass of the current. So in fact, there is a more general setting in which it's correct, this formula, but I just need to show that it is increasing. So I will sketch a proof which uses only Riemannian geometry. So now let's say V is just a smooth manifold in some Rn, and the real dimension of V is D. And I want to show that this is an increasing function. Okay. So, and what is the assumption on V? I need to put an assumption. V is minimal with respect to the Euclidean metric. So now I can sketch the proof. So here is a picture, let's say in R3. So this is the ball of some radius centered at the origin. And I have my manifold V that contains the origin. And I will look at its intersection with the ball of, the sphere of radius T. So I have some manifold here. It's hard to draw, but it's attached on the boundary to this thing. Okay, you have to think of a minimal manifold, so something which is like a wobble like that. Okay, so this here is the boundary of V intersected with the ball of radius T. And here inside, it's V. Okay. Okay, so let's start doing the proof. So look at the volume of V intersected with B0T. So it's a volume, it's a d-dimensional volume. Okay, so I'm looking at this minimal manifold. So now I can compare to something else and say that the volume of the something else is more than the volume of V. Okay, so you just take something which is the following thing. You take a cone centered at the origin with, which is a cone over this set. So it's less than the volume of the cone centered at 0 on the boundary of V intersected with this. So you see something which is just this code. Okay, and what is the volume of this? It's just d divided by d times the volume, so I will comment on that, of what you get on the boundary. Okay, so the boundary here is just the red curve. So if we are in dimension d, if V has dimension d, then here I'm talking of d-dimensional volumes. Here it's a d-dimensional volume, but here it's a volume of this intersection of the sphere with V, so it's a d-1 dimensional volume. And now, how does this volume of the boundary compare to the volume of V intersected with the ball? I can write that it is bounded by the derivative. You know, it's d divided by d times the derivative of the volume, the d-dimensional volume of V intersected with that. Okay, so here I'm using two things. I'm using an explicit formula for the volume of a cone, and then I'm using a comparison or formula for the derivative of the volume. Okay, so there are two steps that I don't want to justify, but which are basic Riemannian geometry. And then you see now you have, if you look at this function, you obtain an inequality concerning the derivative and the function itself. So let's set V of t is volume, d-dimensional volume of V intersected with the ball. Okay, what did I prove? I proved V of t is less than t over d, derivative of V. And I am interested in what? I am interested in the new function t goes to 1 over t to the d, V of t. Okay, and I'm saying that this function is increasing. Yes, of course it is. It's the same inequality as this one when you compute the derivative. Okay, so this implies that this function is increasing. Okay, so I cheated a lot because I didn't show that this function is C1. I didn't show I can take derivative. Okay, I didn't prove this formula, etc. But you see, this is basic Riemannian geometry. Okay. And this basic Riemannian fact has an incarnation in complex differential geometry, which is this definition of Laurent numbers. Okay. Okay. So what is the study of priori subharmonic functions? Okay. So what is the corollary that will be used in the proof of Gromov theorem? Is the fact that a corollary is that the volume of V in the ball of radius t around the origin, so the origin has to be a point of V, is larger than or equal, so what is it? It's t to the d times the volume. So you let t goes to 0, so asymptotically V is like a vector space of dimension d, so it's a volume of the ball of radius 1 around the origin in Rd. Okay, so the Euclidean volume. So there is an explicit formula for that, but this is a positive number. Okay, that's some number which is just given by the dimension. Okay. So this was the proof of the monotonicity formula. Okay, so now I can prove Gromov theorem. So I don't remember the numbers of my paragraphs, but a proof of Gromov's upper bound. For the topological entropy. Okay, so let me remind you, I have a holomorphic transformation of a compact Kähler manifold. And I want to show that the topological entropy of F is bounded from above by the logarithm of the maximum of the dynamical degrees. Okay, so logarithm of the maximum of the spectral radius IC on the groups, on the cohomology groups HPP. Okay, that's what I want to show. Okay, step one. It's another way to define the entropy or to think about the topological entropy. It's entropy versus iterated graphs. So you take gamma in x times x, the graph of F. And then you consider the nth iterate of the graph. Okay. These are sequences in x to the n plus 1 of points such that when you go from xi to xi plus 1, you are always in the graph. Okay, so let's say like this, in xn, such that xi plus 1 is in gamma for every I less than n minus 2. Okay. So if you prefer, it's just set of points x, f of x, f of x, fn minus 1 of x, for x in x, as a subset of x to the n. Okay. I mean, this fact is equivalent to say that to go from the first to the second, I'm taking f, and then I'm taking f again, and so on. Okay? Okay, so that's the definition of the iterated graph. Now let me define what I call epsilon cube. By definition, epsilon cube in xn is just a product of balls of radius epsilon. Okay, so I take a ball in each of the, so I have, let's say, x times x. You take a ball here in x of radius epsilon, a ball here in x of radius epsilon, you take the product. Okay, this is an example of an epsilon cube when n is equal to 2. Of balls of radius n, of radius epsilon in. So if you prefer, you can put, as a metric, you put the maximum of the metric on each factor, and you take an epsilon ball for this metric, for the max metric. And then you define some kind of covering number by epsilon cubes. So Gromov call it the capacity of the graph I mean, the nth iterated graph at scale epsilon is the minimal number of epsilon cubes needed to cover the graph gamma n. Okay, so, and I will take epsilon cubes centered at points of gamma n. Okay, so you have your iterated graph. I draw it in dimension 2, but you should imagine that it's very large dimension because it's an iterated graph. And so you try to cover it by cubes centered at points of gamma n. And you put the cubes in such a position that you minimize the number of cubes that you need. Okay? Okay, it's the same as covering gamma n by balls for this max metric, you know. But then you are trying to find points on the graph, which are the centers of these cubes, so some points, such that the epsilon cube centered at these points covers the graph. But what are the points which are epsilon far from a given point on the graph? So if I look at the graph, you know, I have x, f of x, f to the n minus 1 of x. I take another point on the graph. And if I say that those 2 points are in the same epsilon cube, what I'm writing is that the distance between x and y is less than epsilon. The distance between f of x and f of y is less than epsilon, and so on up to fn minus 1. So these 2 points are in the same, I mean, let's say the second point is in the epsilon cube centered at x, if and only if x and y have the same orbit at scale epsilon up to time n. Okay. So this covering number is the same as the number of balls I need to cover x itself for this iterated metric. Okay. And so the topological entropy of f is nothing else than the, at scale epsilon, that the supremum limit as n goes to infinity of 1 over n log of this number. Okay, it's just an equivalent point of view on the notion of topological entropy. And so the topological entropy is a limit of this when epsilon goes to 0. Okay, so that step 1 was just this, just a reformulation of topological entropy. Okay, so now I will introduce 2 new quantities. I want to compare this number of cubes I need to cover my graph to the volume of the graph. Okay, so I will do some basic geometry comparing covering numbers and volumes and densities, things like that. Okay, so now I do Riemannian geometry. So on x to the n, we put the product metric, the product Riemannian metric given by the sum I mean, at the level of Keller form, it's given by the sum of the pullback of the Keller form. Okay, so let me maybe be more precise. So I have x to the n. So I have n projection onto x. And on x, I put the Keller form, I fix a Keller form kappa. So, okay, x is Keller, so I fix a Keller form kappa. And I define a new Keller form kappa index n is a sum for I equal 0 to n minus 1 pi I star of kappa. I pull back this. Okay. Okay. And this is the Keller form I will use on xn. And the Riemannian metric I use on xn is given by this Keller form. But I gave an example at the very beginning. You know, if you do it just for Euclidean spaces, so you start with a Euclidean space, let's say the one-dimensional Euclidean space, which is given by the complex line. X is now c to the n. And this Keller form is just the sum of the Keller form I had in one variable, and the metric given by that is just the Euclidean metric on c to the n. At the level of Riemannian metric, let's say the norm of a vector u1, un, where each ui is in a tangent space of x, the norm square is just sum of the ui square. Okay, it's a standard round Riemannian metric. Okay, so this is the metric I will use. And now I want to compute the volume of the graph, the iterated graph. So I compute it. So with respect to this Keller form kappa, I will not write the index n, it is here. Okay. And I look at the exponential growth rate of this sequence of numbers. So I take log of that, divide by n, and then I take lim sup of this as n goes to infinity, and I say that this is logarithmic volume growth of my sequence of graphs gamma n. Okay? So I will use the notation of Gromov, it's log of gamma. Okay? Okay, so that's the first quantity I can look at. Second quantity is local density at scale epsilon. Okay, so I can look at the following thing. I take a point z in gamma n. I compute the volume of gamma n intersected with the ball of a radius epsilon centered at z. Okay, so here it's the ball with respect to the Riemannian metric given by this Keller forms kappa. And here it's the volume, so gamma n, its dimension is just a dimension of x because it's parameterized by x, f of f, x square of x, and so on. Okay, so here the dimension is a complex dimension. What is the dimension of x? Dimension of x is capital M. It's little m, so it's volume in real dimension to m. Okay. So that's what I see in a round ball around the point z. It's the volume of this piece of the graph where the radius here is epsilon. And this I call the density of gamma n let's say, density of gamma n at scale epsilon centered at z. Okay. And I take the minimum of that over all possible points in gamma n. So the density of gamma n at scale epsilon is the minimum of this as z varies in gamma. Okay. So you see you have your graph gamma n and you choose a point, compute the local volume, and then you move the point along the graph and you take the minimum. Okay, so this is a second number, and then you can look at the exponential asymptotic behavior of these numbers. So you define the logarithmic asymptotic density of gamma at scale epsilon to be the limit, I mean the infimum limit as n goes to infinity of 1 over n log of the local density of gamma n at scale epsilon. Okay. So here it's an infimum limit because you see these densities, I'm zooming in very small balls of radius epsilon. So locally, I expect the volume to be small. So this is less than 1. This is what I expect. So this log is negative, and I take an infimum limit. And then you have a basic inequality. Okay, I will try to prove it without making a mistake. Okay, I need to take this. Okay, I say that I take S in gamma n be a maximal finite, I mean it's finite because gamma n is compact subset of points zi such that the balls centered at the zi and of radius epsilon are pairwise disjoint. Okay. So I take such a set. And so because these balls are disjoint, if I sum the local densities, I get a number which is a lower bound for the volume, the total volume of the graph. Okay, so I said the volume of gamma n is larger than the number of balls, which is a number of elements in S, times the minimum of the volume I can see in each of these balls. You see, these balls are disjoint, so each ball intersects the graph on a subset with volume at least this density. And because they are disjoint, I can add up all this volume and I get a lower bound. But now you know this. I took S to be maximal. So every point in my graph, it has distance less than epsilon from one of these points. Because otherwise I can add a new point. And so this number is larger than the optimal number that I can get to cover my set by cubes. The point is that cubes contain balls. Okay, so this is a basic inequality. So now you take logs, you divide by n, you take limits, or supremum limits, okay, and you get what? You get, so this contributes as topological entropy. Okay. Then I put this term on the left. These contribute to the logarithmic volume. And this density here contributes to the logarithmic asymptotic density, but there is a minus sign because I put it on the other. Okay, so this is the basic inequality. So you see, up to now, I have not done anything impressive. You know, I just looked at the definition of topological entropy and used the fact that I can reformulate it using this covering number. And then I just used this argument that disjoint balls contribute independently to the volume. Okay, so nothing happened up to now. But the two things or maybe there are two epsilon missing, no? Here, one here, at scale epsilon, yeah? Okay. So if I prove that this is 0, then I get an inequality with the log of the volume. I can take limit as epsilon goes to 0, and I will get topological entropy bounded from above by the logarithmic, the exponential growth of the volume, okay? So first I will prove that this is 0. And then I will prove that this is the max of the the dynamical degrees. And the log of the dynamical degrees. Okay, so I have two steps. I need to prove this is 0. I need to estimate this in terms of dynamical degrees. So step 3 will be the description of the local density. How can I show that this asymptotic density, at the logarithmic scale is 0. Okay, so step 3. This number is 0. Why? Okay. It's because okay. Let me write it again. What is the definition? It's limit, infimum limit when n goes to infinity, 1 over n, log of what? Of gamma intersected with the ball of radius. Okay, so I have a minimum and a thing like that. So let me write it like that. Density at scale epsilon of gamma. Now, you see, gamma n. Gamma n is in x to the n with this scalar form kappa n, which is the sum of the pi star kappa. Okay. Forget about this strange geometry. Assume that, in fact, X is just a complex vector space, and these scalar forms are just the usual Euclidean metrics. Then I proved with the monotonicity formula that this density is larger than what? Epsilon to the dimension of the graph, so D. Here, no, it's M, sorry. So M is the complex dimension. The real dimension is 2M, times the volume of what? Of the Euclidean ball centered at the origin of volume 1 in R2M. Okay, so if everything was Euclidean geometry, flat Euclidean geometry, I will get this lower bound. Okay, and this is just one number, you know. Does not depend on n, it depends only on the dimension. And this depends only on epsilon, it does not depend on n. So if you take the log and divide by n, this quantity will go to 0. Okay? So if everything is just Euclidean geometry, it's easy. But now you just have to compare, you know, locally, you take your Keller form, and in charts, it's bounded from below by some small number times the Euclidean metric, and it's bounded from above by a large number times the Euclidean metric. Okay, and this quantity, you do it in X, and then when you do it in a product, you get the similar upper and lower bound. Okay? So it's just what I did in Euclidean geometry, and then some comparison which is uniform in N. You compare kappa to the Euclidean metric in charts, in local charts for X, and then you get uniform comparisons for X to the N, and you get the result. Okay. So I let you write the details because then you have to write some upper bound, lower bounds for volumes, but this is easy. You lost, Stefan, or you? No, it's negative, but because you take the log of a small number. No. This quantity, the density, is positive. It's a volume. Okay? So this quantity is positive. It's a volume. But it's bounded from below by a small number, but a number that does not depend on n. When you take the log, it's negative, but bounded by something which does not depend on n. And then you divide by n. Okay, so this proves that this here minus log epsilon gamma, this is bounded from above by 0. Okay, so that's step 3. And step 4 is what? Step 4 is computation of volumes. Okay. Okay, so I want to compute these volumes. Do you have a question? You have a question? Okay. Do the exercise to write the details. It's very easy once you have that. Okay, so now the last step. I want to compute the volume. So what is the volume? So I want to compute volume of gamma n. Okay, so gamma n, its dimension is a dimension of x. So it's 1 over factorial of the dimension, integral over gamma n, kappa to the dimension. So kappa is the Keller form I use on xn. Okay, and kappa n is the sum of the pullback of kappa. Right? Okay, so that's the formula by Wirtinger. But I know how to parameterize my graph. Okay? So I can transfer this formula as an integral on x, because gamma n is just parameterized by x, f of x, up to fn minus 1 of x. This is how I parameterize gamma with x in x. Okay. So this integral is the same as 1 over factorial m, integral over x. I pull back this form, and I get kappa plus f star kappa plus second iterate of f star kappa plus etc. up to the n minus 1 iterate of kappa, and then I need to take the m's power. So you see now this integral is an integral over x of Keller form to the m, which involves only kappa and f star. So we are in a good shape to prove what we want. Okay. And again, this computation, I can do it at the level of homology groups. Okay, so how does it work? So maybe it's easier if I do an example. Okay, so example. Let's say dimension of x is 2, so my m is 2. What do I get? So 1 over 2 integral of x. And now I will take, let's say, take n equal to 3. Okay, so I have kappa plus f star kappa plus second iterate of f star kappa to the m. M is 2. Okay, so this means I need to take the wedge product of this form with itself. Okay, so let's expand this integral. What do I see? Okay, so kappa wedge kappa. Okay, so let's do this. So kappa wedge f star kappa. And then kappa wedge f2 star kappa. Okay, and then I continue f star kappa wedge kappa. Okay, so this is symmetric. These are two forms, so I can permute. So I get 2 here because of this term, and then f star kappa plus f star kappa. Okay, so times f star kappa. Okay, so f star kappa wedge f star kappa. This is f star kappa wedge kappa. And then f star kappa wedge f2 star kappa. This is f star of kappa wedge f star kappa. Okay, I'm using that f star kappa wedge f star kappa is f star of kappa wedge kappa. I continue. f2 star kappa, so I already saw here. f2 star kappa wedge f star kappa is here. And then F2 star, wedge F2 star is okay? So this is the type of computation we need to do. And what do we see? You see, I see something like that. Kappa wedge F2 star kappa. So in general, if I do it n times, I will see things like Fn star kappa, or Fn minus 1. This will enter into my computation. Okay. Then I see also F star kappa wedge kappa, but also I see also F2 star kappa wedge kappa. So I will see things like F2, Fn minus 1 star kappa wedge kappa. This I will see in my computation. And then I see mixed terms. Okay. Here, kappa wedge F star kappa, but I pull back by F star. Okay. So what happens asymptotically? So you see terms like that. I'm still assuming that the dimension is 2. So terms are not n large. Okay, you will see things like kappa wedge F J star kappa pulled back by FL star altogether. Okay, with a constraint which is J plus L is at most n minus 1. This is what you see. Okay. But this type of things, you know, it's asymptotically, it's bounded by FL star acting on what? Acting on forms of top degree. So here on H22 times Fj star acting on forms of type 1,1 times what? Something would depend only on kappa. Okay. No, in fact, I should write kappa square, something like that. Okay, and some uniform constant. Okay, then you take the log, you divide by n, and you take the limit. Okay, and you want to understand the asymptotic growth of that. So when you take the log, you take the sum of the logs. And when you divide by n and take the limit, what is the term which is winning? The largest one. The largest one is the maximum of the lambda p. Asymptotically, you take log, you divide by n, it's less than max log lambda p of f. Because J plus L is less than n minus 1. Okay, so I did the proof. So I cheated a little bit. Of course, what I was, this control is the control of these terms. But you also have the constant terms in front of this. But these constant terms are binomial coefficients that, okay, of degree at most m, at most the dimension of the variety. Okay, so these terms, you control them. They grow polynomially with the number of iterates. So when you, okay, that's it. Okay, so that's the proof when the dimension is 2, and I let you write the proof when the dimension is arbitrary. At this stage, the proof is just multilinear algebra. Yes? Excuse me? Yes. So this argument tells you that this is less than max lambda p of f. And the step 3 says that this is non-positive with a minus sign. Okay. I cannot hear you. Yes, it is equal to 0. But I just proved this is non-positive. Okay, so this is the end of the proof of Gromov theorem. So the proof itself is not so difficult. Okay, step 1, you cover the graph by cubes. Step 2, you prove the basic inequality, which is just what happens when you have disjoint balls. And then comes Keller geometry, okay? Step 3 is complex manifolds are minimal in Keller geometry. And by the monotonicity formula, you get that this local density does not decrease exponentially fast. Okay. And step 4 is just the Wirtinger formula plus a basic estimate, which are like, it's just multilinear algebra. Okay? But putting all these things together, I mean, this is quite impressive, okay? It's a very nice argument, I think. Okay. So now so this is, why did I prove this, this statement? I wanted to explain that from a dynamical point of view, these numbers are related to crucial notion from dynamical systems. Okay, this dynamical degree, they tell you what is the topological entropy. If you know the topological entropy is positive, then you can start to use a lot of tools from dynamical systems. So you can construct stable and unstable manifolds. You can construct, in good situations, periodic points, things like that. Okay. So it's very crucial to know this just to start studying the dynamics. Okay, so now I will start a new part. It's like a new lecture. I will talk about something else, but still related to dynamical degrees. Okay. I started one. Okay. So I want to discuss. So if you were lost with my differential geometry arguments, now I will do algebraic geometry. Okay. At some point, I will even say flat, but not in the Riemannian sense. Okay. Okay. So it's part 2. So let me remind you that lambda p of f is what? It's the limit when n goes to infinity of, or you iterate f n times, you take a hyperplane section, you take the section p times, you pull back by f, you intersect with m minus p, okay, where f from x to x is a dominant rational map, I mean self-map, or transformation from x to x. X is a projective variety in some Pn of dimension equal to m, and H is a hyperplane section of X. Okay, and so this limit, sorry, you need to take the nth root. This limit exists, does not depend on H, is invariant under birational conjugacy. This has been proved last week. Okay. But you need to define correctly this intersection product. So what do? You have f from x to x. You take the graph of f. So there are two projections. Let's say epsilon. So I will use Greek letters for this projection. So now epsilon is a birational, is a morphism, and pi. And this is what? So you take, okay, so you do it for Fn. That's the graph of Fn in x times x. And you pull back HP, you pull back H m minus p by epsilon. And you intersect this in the graph. And you take the nth root. Okay, so the intersection is here. So you need to intersect. So I assume the graph is normal. So you need to intersect in this normal projective variety, or if you are in characteristic 0, you can take a resolution of singularities and intersect on it. Okay, and the relationship to what I was saying before with Gromov theorem is that this is also equal, I mean, this number is equal to the integral over x minus the indeterminacy locus of f, iterated n times, of fn star of, so you pull back the Fubini-Studi, form, and you intersect like that. Okay, so this number before taking the nth root is equal to this number. Okay, you just have to pull back the Keller form, the Fubini-Studi form, by f, where f is well defined. So outside the indeterminacy set, you just integrate outside the indeterminacy set, you get the same number. Okay, so this equality holds when x is a smooth complex projective variety in Pn. Okay, so this is a relationship between the two notions. But now I don't need to assume that x is a complex manifold. It works over arbitrary fields. And so last year, Junyi Xie proved the following. If, how to call it? So if you have a family, so you have a family of dominant rational maps over some base S. Okay, so this means, I mean, this implies that for every S in S, you can look, let's say this is the projection P, or P is bad, Q. So you look at the fiber x sub s, which is q minus 1 of s, the fiber at s, then you get a map f index s from xs to xx, which is a dominant rational map induced by f. Okay, so I don't want to make precise exactly what assumption I have on this family, but say this is a notion that Michel and Ronan, I think, also introduced. Okay, so if I have such a family, then for every p, the function s goes to lambda p of fs is a semi-continuous in the Zariski topology. Stefan, you have a problem? What is the problem? Did you do that? It was always the same space for you? Oh, okay. Okay, so it's more general than that. I really want something more general. Okay. Yeah, yes, at the same time, yes. I will explain that, okay? So I want to, that's what I want to do. So I started like 1 hour ago, or, okay, so I have like 25 minutes, excellent. So you will see. So what I want to do today is just discuss what should be the right statement on examples, okay? Show phenomena that explain that you cannot expect more than semi-continuous. It cannot be continuous. And so I just want to give examples. So I have 25 minutes. I will give some examples. Okay. Oh, before I do that, sorry, I want to give at least one consequence, because I will spend most of my time discussing this theorem now, which I didn't state properly. But why should we care about this semi-continuity property? Okay. Here is a corollary of this statement. So you take a rational dominant transformation of, let's say, complex projective variety. X. Okay. And then you assume that there is a unique maximal dynamical degree so in the following sense. So there is one dynamical degree which is strictly larger than all the others dynamical degree. Okay. In particular, this dynamical degree is larger than 1. Then for every u in X Zariski dense open subset, the set of periodic orbits contained in U is dense in U. So this assumption, let me remind you that if I look at log of lambda p as a function of p, okay, the Hodge index theorem implies, or Rovansky-Tessier inequality implies that this sequence is concave. Okay, it looks like that, the log of the lambda p. This assumption that there is a unique lambda p which is larger than the other ones means that there is no flat like this. So it has to be like that, you know. So this is the maximal. If you see some flat, then you cannot apply the theorem. If you don't see one and you have a unique maximum, then you can apply the theorem. Okay, second remark. So you have X. So that's your variety. You have your rational transformation. And now you want to remove a set. So for instance, you remove all indeterminacy points and the exceptional set. Okay? But you can remove more. So for instance, you have a subvariety you like and you want to remove it. Okay. Then the theorem tells you that you can construct points in the complement of this Zariski closed set such that the orbit of the point is completely contained in the complement of this set and is periodic. Okay. Okay. And you remove the indeterminacy points because when we talk about periodic orbits, you want orbits which are well defined. And not only you have one of such points, but the number of points is very large because it's infinite because it's Zariski dense in X. Okay, so that's the statement. And in fact, to prove this statement, when you use these techniques I will describe in my lectures on p-adic dynamics, p-adic methods. In fact, you change the field of definition. Instead of using complex numbers, you use other numbers, and then you use reduction modulo p, and so you prove the statement modulo p. So imagine X is defined over the rational numbers, and F is defined by formulas with integral coefficients. You take p large, you reduce mod p, and you prove the statement modulo p over fp bar. And here it's much simpler because over fp bar, every orbit is finite. And then you, from what you get on fp bar, you want to come back to a statement on X. And what you do for that, you apply specialization techniques, and you need to use this semi-continuity in the Zariski topology now over spec Z. Okay? So I didn't say what is S, but you see, S, I want to be able to take spec Z. Okay? So that's one consequence of this theorem, which is beautiful. Okay, so now I want to discuss examples. No. Zariski dense. No, in the analytic topology, this is not correct. Okay, so I just want to describe examples of families and what happens with these degrees or dynamical degrees. Okay. Okay. First example is the following one. Okay, Okay, so you take a cubic curve. Here in Weierstrass form, okay? So that's my cubic curve. Okay, so coordinates x and y, in fact, in P2. Okay. And the point on the line at infinity is an inflection point. I take it as the zero of my elliptic curve. Okay, so it's a cubic curve. An elliptic curve. If it is smooth, like this one. And then I can look at the following geometric construction. I take a point on my curve. I take the tangent to the curve at that point. I get a line, and now I get a new point on my curve. Right? Did you understand the construction? If I take a point on my curve, I draw the tangent line, I get a new point on my curve. Okay. This point is equal to that one if my starting point is an inflection point, like here somewhere here there is a fixed point. Okay, right? So this, in terms of elliptic curve, so if I use the group law, what is this map? Okay, I take a point Z on my curve. What is this point for the group structure? It's minus 2Z. You know, if you take a line and you cut the curve with a line, the sum of the point on the line is equal to 0. That's a relation. But this point here the curve cuts my line with multiplicity 2 at this point. So I have 2Z plus this point equals 0, so this is minus 2Z. Okay. So what the transformation I'm looking at is Z goes to minus 2Z. Okay. On a curve which is an elliptic curve, so over the complex number, I can write it like C divided by some lattice to C divided by this lattice. Okay. Okay, so it's just dynamics on a curve. So what do I have? I have just lambda 0 and lambda 1. Lambda 0 is always 1 for a dominant map. Lambda 1 is what? Is the topological degree here. So I need to compute how many preimages I have for this map. Okay, so you need to solve minus 2Z is equal to something modulo the lattice lambda. And you have 4 solutions. Okay, so this you know also from algebraic geometry. If you take a point on the curve, W, you look for lines which are tangent. So where is it? Here there is one. Tangent to my curve, and these points are mapped, this one here and this one here, I mapped to W. Okay, here I see only 2 lines because it's a real curve, but over the complex number you see 4. Okay, if I take a curve like that, I take a point here, I will see 1, 2, 3, 4 preimages. Okay, let me. Okay, so it's an example of an algebraic dynamical system on an elliptic curve, multiplication by minus 2, lambda 1 is 4. Okay, so that's some of the most basic example. And now I do a family. Okay, so my family is like that. So you understand what I'm doing? I'm doing a pencil of cubic curves in Weierstrass form. Okay. But one of the curves is singular. So this one is singular. Okay. Now I can define a rational transformation of P2. I take a point in P2. Here, okay, it's on one of my curves. I take the tangent line, and I intersect with the same curve. And that's my map. It's z goes to minus 2z along each of the curves. And I want to understand the dynamical degree when I restrict to one of these curves. Is it clear? Let me draw this drawing one more time. So again, I take a point on the plane. I look at the curve in my one parameter family containing that point. I take the tangent line, and I take the point of intersection with my curve. Okay. When the curve is smooth, the restriction of my map to this curve has lambda 1 equal to 4. This is what we did. What happened to this when I restrict to this curve? Okay, so when I restrict to this curve is a P1 with 2 points which are identified. Okay, so 2 points which are identified in P1. Here it's multiplication by minus 2. When I go to the limit, I get W goes to 1 over W square. You know, the group law of the elliptic curve becomes the group law on C minus 0, the multiplicative group. Now the topological degree of that, or if you prefer lambda 1 is not 4, it's 2. Okay, so geometrically, if you take a point on this nodal cubic curve and you look for tangencies, you find one here, but not more. Okay, so this real picture is not very convincing because already for elliptic curves I could find only 2, but if you do the computation, you find just 2. Okay, so you see the lambda 1 for the general curve, it's equal to 4. When you specialize to this nodal curve, you get 2. So you get a semi-continuity. Okay, the generic value is 4, and at the spatial value, it drops below, it's 2. Is that clear? Okay, I want to understand this phenomenon. Okay, let me see. Okay, so what's happening in this picture? It's very geometric, you see. When you take a curve, a smooth elliptic curve in your one parameter family, which is very close to it, what happens to the tangent line? You know, you compute your tangent line here, you move, and here, near this singular point, you make, whoop, almost a quarter of turn in a very small, I was about to say in a very small period of time, you know, when you move along your curve, you turn by 1/4 of turn like this. Which means that if you look at preimages of a point here, you know, let's say of a point here, you get preimages coming from here. When you move here in this very small region, the tangent line intersects here in a very large region, your curve. Okay. So what does this very geometric picture tell you? It tells you that if you look at this map multiplication by -2 along this pencil, this point is indeterminate. And the image of this point will be the entire curve here. Okay. In fact, more precisely, this point will be mapped with multiplicity 2 on this nodal curve when you resolve the map. Okay. So what I'm saying is that this map from P2 to P2 is rational. It preserves this pencil of curves. On the general curve, lambda 1 is 4. On this special curve, lambda 1 is 2. But this indeterminacy point give rise to a curve by resolution of indeterminacies, which is mapped twice on this curve. And 2 plus 2 is 4. Okay? So this is exactly the type of phenomena that we are trying to understand when we do families, and which is contained in the theorem by Junyi. So now I give a second example. Okay, so here to come back to this, in this example, X was P2, but the map Q to S, so S was P1, the parameter for the pencil of cubic. Okay. But this map is not well defined because two cubics, they intersect in 9 points. So in fact, this map has indeterminacy points. So in fact, I should take for X P2 blown up at the base point of the pencil to get a regular map. And then I can apply this theorem. Okay, so now here is another example. So sigma is a standard Cremona involution. A is an element of PGL3. Let's say I use complex numbers, but this is not so important for the moment. Okay. And so PGL3 will be S. Okay, so it's my parameter space for my family of maps. And F index A is just A composed with sigma. So what is the geometry of that? So this is a picture we already did a lot of times. So these are the coordinate axes. So sigma, its indeterminacy points are the coordinate points, the toric points. So here you see, let's say, point P, Q, R. Okay, these points. And the exceptional locus of sigma is made of 3 lines, let's say Lx, Ly, Lz, where Lx is this line where x is equal to 0. Okay? But when you apply sigma, this triangle is mapped to this triangle, but then when you apply A, it moves. As well. So let's say P moves to a point P1, which is A of P, and then Q moves to a point Q1 and R to a point R1. Okay? That's our map. And now you start iterating this map. Okay, so I want to iterate this map. So this map here is a map of degree 2. And then I apply FA again. So I need to look at, the question I'm interested in is, for this birational map, what is lambda 1? Okay, so I need to compute the degree of the map, the degree of the second iterate, and so on. And you know that if the map is algebraically stable, which we saw last week, then the degrees are multiplicative. So what does it mean to be algebraically stable? It means that you look at the curves which are contracted by your map. So for instance, Lx is contracted to R, and then R is mapped to R1. Then you apply F again. So you apply sigma to this point, it moves somewhere, and then you apply A. So you get a point R2, and you do it again and again. If these points, they never come back to the indeterminacy point of your map, then it is algebraically stable, and the degrees are multiplicative. So if okay, so you look at this orbit, so if it never comes back in the set PQR, then degree of Fa to the n is equal to 2 to the n, and lambda 1 equals 2. But if at some step the degree, the point comes back to the indeterminacy point, then there is a simplification in the formulas. You can factor out the equation of a line, and you get the existence of some n0 such that degree of Fa to the n0 is strictly less than degree of Fa to the n0. Okay. If it is not algebraically stable, you get these strict inequalities. And then, automatically, lambda 1 of Fa is strictly less than 2, because lambda 1 is, it's a limit, but it's also the infimum of degree of Fa to the n, 1 over n. So this limit for submultiplicative sequence is also an infimum. So if at some point you have some drop, some decrease, then you get a strict inequality. And so you see this phenomenon is semi-continuous because you take a generic A. For a generic A, this orbit of points will not come back to PQR. But for very specific A, it will come back. And if you write the equation that it comes back after n0 step, then this becomes an algebraic equation on the parameter space A. And so the statement of the semi-continuity theorem tells you that it is always like that. So here, I think I have 2 or 3 more minutes, or not? Not. Okay, so I will stop here. I mean, the semi-continuity in this family, this explicit family, I think it can be proven independently of Junyi's result, but I think nobody did that. Okay, but in fact, this theorem by Junyi, he first proved a version for birational transformations of surfaces, which is easier to understand, and then a version for in this degree of generality. But so the type of phenomena you see behind this result is this type of behaviors. Okay. Okay, so tomorrow I will sketch the proof of Junyi's result, and that will be it. And for the periodic things, I still have 2 lectures. No? Oh, yes, yes. Yeah. Yeah, you can find a way that works. Here. Yes, it's easy. Let me try to cook one. Okay, you see, let's look at a very particular case. So let's suppose that this triangle, in fact, is like this one. I mean, green is not good. Where is my red? Okay, so you see this line here, Lx is mapped to this point, and this point is mapped, say, here. Okay, this line is mapped to this point is mapped here, and etc. Then what is the image of this point? This point is on this line, but is not an indeterminacy point, so the map F is well defined here. It maps it here and then back here. Okay, so in fact, these points, they have a finite, they never come back here. Okay. Okay, so but you see it's completely geometric, and in this configuration, you know that the map is algebraically stable. So it's a general idea. If you want to construct maps for which you know that you want to prove that the indeterminacy, the image of the exceptional locus never visits the indeterminacy points. You just have to control the orbit of these points. And for instance, if they are contained in the zone, in the region of the space where the map is attracting, then you control the dynamics and you never come back. But you see here, maybe I can add one thing. Assume everything is defined over with integer coefficients. So now A is in PGL3 with integer coefficients. So it's defined over the integers. Take a very large prime P, reduce mod P. And so you have your dynamical system on P2, but now also over on P2 over Fp. The indeterminacy points, they come from this point which are 1, 0, 0, 0, 0. So you see them over Fp. Okay. But now over Fp, the Fp points are finite. So at some point, the orbit must come back to the indeterminacy points. Okay, so if you reduce this map mod P, you always have some simplification in the degree growth. It's never algebraically stable. Okay, so again, this is an instance of this semi-continuity result over spec Z. And you see semi-continuity in the sense that the limit of the lambda 1 mod P is equal to lambda 1 of F over C, but only at the limit. Okay, so here you can think about this example as an example where the parameter space is a set of 3 by 3 matrices, invertible ones, or you fix A with integer coefficients, and the parameter space now is spec Z. Yes? Oh no. You mean for which type of examples? Oh. Yes, so here is another way to think about what you say. I can look at a surface which with an elliptic fibration. So a genus 1 fibration with a section. And some of the fibers are singular fibers. And then you can look at multiplication by D along the general fiber. So you get a dominant rational map, self-map of your global surface. And so at the generic fiber, lambda 1 is D square. And you ask what happens at singular fibers. Okay. If the singular fiber is the simplest thing, like such a nodal curve, then you get D instead of D square. This is basically what I did here. But you know you have this list of possibilities for the singular fibers due to Kodaira, or I mean you can reduce to a finite simple, I mean a simple list, or Néron models. And then you can also do the computation in all cases. Yes, I mean basically this is Néron did it. For all the possible types of what is the vocabulary, stable degenerations, or I mean, Néron models. I mean, but for what I'm saying is for elliptic curves, okay? I'm not saying that for a billion varieties, and for a billion varieties, I think you did it, or Sasha Kuznetsova, she did it with Charles, okay? Okay, so it's not easy, but this has been done, okay? Yes, it's more than that, it's constant. So if you have, hope what I'm saying is correct. So let's say you have a complex, projective variety with a submersion onto a base, and you have a regular endomorphism of the projective variety, preserving the fibration. Then you can compute lambda 1 fiber by fiber, and this should be constant. Okay. But what may happen is that you have such a family when you restrict your transformation to each individual fiber, you get a well-defined map. But in family, it's just rational. This can happen. This I will give an example tomorrow. Okay, and in that case, dynamical degrees they can drop. Someone else, yeah. Easy no. If the question is, did someone do that? I did it with Jérémy Blanc, but we never published it. And oh, so you wrote the chapter about that. Okay, so this is done in Stefan, and maybe also in the article by Anna Bott. Okay. Okay. So this has been. Yeah, this has been done by Stefan in his book, in the book. In the book, yeah. It's very nice, yes.